Hey everyone, so we're going to talk about the next unit, which is all about energy. Now, what is energy? You've probably heard it before in various classes, and a lot of you have used it in some of your explanations. So let's get an actual definition. Energy, which is represented by the symbol E, is the ability to do work on an object. Okay, so what does work mean in the context of physics? Well, work, which is represented by the symbol W, is the ability to change an object's energy. You might notice that that's a circular logic. It turns out that work and energy are essentially the same thing, that energy allows us to do work, and work allows us to change energy. Now, another way of actually describing work is the ability to actually displace an object over some sort of distance. You can by applying a force to it. So that's kind of like another way of thinking about work. That work allows us to essentially move an object from one point to another in a specific way that changes its energy. Um, a perfect example of this is usually lifting an object up or sliding the object to the side. When you lift an object up, you're changing its energy, and depending on how you slide an object to the side, you could also be changing its energy. Uh, we're going to be talking about all the different types of energy in this video. So we're going to go through kind of the main ones and go into a slight more deep dive with the concept of work. But the one thing to keep in mind is work is a type of energy. So a lot of times people think that because of the name work being different than energy, not having like being called work energy, that it's not the same. So just keep that in mind that work is a type of energy. So, some of the other types of energy you might have heard of potential energy. Potential energy in this class is represented by the symbol U. Why? I don't know. So, U represents potential energy and is usually defined as stored energy. This means that the energy can be stored and used later to be converted into energy of motion or heat. One thing to point out, there's multiple types of potential energies. We're only going to focus on about two of them. We're going to talk about gravitational potential and spring potential energy. But there are other types. There's electrostatic potential energy, the magnetic potential energy. There is chemical potential energy, which we definitely don't talk about. And they all kind of work the same way. The idea being that the energy is stored in some other force. Uh, as you could probably guess, with the gravitational potential and spring potential, what that force might be. The next type of energy is kinetic energy. Kinetic energy is represented by the letter K, and it is the energy of motion. This means that whenever an object is moving, it has kinetic energy. One thing I actually want to go back with the concept of potential energy is I mentioned that it was stored energy. I want to clarify that that doesn't mean that the object might not have kinetic energy. An object can actually have multiple types of energy. A common misconception people have is that an object that has potential energy has no motion to it, that it is motionless and it has zero kinetic, and that's not the case. Just keep that in mind. You'll see what that means in a few seconds when we start going over the different types in with the equations. And then one of the last types of energy that we're going to talk about is heat. Now, the only thing that you have to know about heat is that it is essentially the lost energy. It's energy that gets lost through things like friction and all that. It goes by a variety of different names. It could be called heat, sometimes called internal energy, the energy being done by friction, the work being done by friction, a variety of different things. It's used with the symbol Q, and basically, it's the idea that, like I said, whenever we kind of make a conversion, because there's always friction involved, there's always going to be a little bit of energy being lost to heat as somewhat of like a tax. So anytime we kind of do something in a problem, we get taxed a bit of our energy that we have. So just keep that in mind. A lot of times we're going to almost ignore heat unless said otherwise. So there are going to be times where we're just going to pretend like heat doesn't exist, that there is no energy being lost to friction, because like I said, sometimes it's easier just to deal with these scenarios as if there was no friction. But then there are going to be other cases where you have to keep in mind that it is a possibility that there could be heat, there could be energy being lost to friction, and usually this comes with some sort of imbalance. And I'll explain that when we get to the conservation aspect. All right. One thing to know about all types of energy is that they're all measured in the same unit of joule. Joule is represented with a capital J. So the unit for energy is joule. This includes potential, kinetic, heat, work, and just energy in general. Energy is a scalar, which means that direction does not matter. So unlike all the other cases where we had to be very clear about direction and sign, energy is not going to be that same case. It's a scalar, so direction doesn't matter. There's no such thing as having kinetic energy of 50 joules to the west. However, there is such thing as positive and negative energy. You could think about how this works, but I'll tell you right now that the idea is with energy, positive and negative now means adding or subtracting or um, increasing or decreasing in your energy. So if you have a potential energy of a positive 50 joules, that basically means that you've added 50 joules of potential energy to the system. If you have a potential energy of negative 50, that means you've lost 50 joules of potential energy. All right. Usually, though, we would normally talk about this in the case of change in energy. So your potential energy changes by negative 50 joules. Or in the case of work, because that is a change of energy, you could have work being a positive value or a negative value. So let's actually go back to work because this is kind of the basics of everything. So, like I said, work in a lot of cases can be positive or negative because it could either be giving us or taking energy away from the system. So, positive work is essentially it's giving energy to the system. If I push an object to make it go faster to increase its kinetic energy, you would say that I'm doing positive work onto the system. On the flip side, negative work basically means that the force is actually going in the opposite direction that it's moving. It's taking that energy away. So it's decreasing the system's energy. So taking an object that is high up and has a lot of this potential energy and bringing it to a lower point would be me doing negative work as I kind of bring it down and decrease the potential energy in that system. Now, in order to do work, this is actually extremely important to keep in mind that the force that gets applied to an object has to be acting parallel to the direction that the object is moving. So the object has to be displaced, and the force has to be applied in parallel or anti-parallel directions. So either in the same direction or opposite direction, or they need to have some sort of component going there. If the force and the displacement are in completely different dimensions, one's going in the x direction, one's in the y, then our work is going to end up being zero. A lot of times, this is written as the applied force is going to be parallel to the displacement. Now, I wrote specifically the applied force because a lot of times when we deal with work, it's usually seen as the work that a person is doing onto a system. So the work that I do to move an object, the work that I do to lift an object up, that force that I apply is what we call an applied force. However, technically, the work is defined as the work being done by any specific force. So if we wanted to know what the work being done by the gravitational force, then the force would be Fg. If we want to know what the work was by the frictional force, then it ends up being Ff. So a lot of times the work is going to kind of have some sort of uh, qualifier of what type of force we're looking at. So whatever they say, the work of blank, that's the type of force we're going to be looking at specifically when we do our calculations. Now, the equation ends up being work equals force times displacement. That's what this D is representing, displacement, times cosine of theta. Uh, the reason being is because we need to get the force in the same direction, in the same plane, and parallel to that displacement. So if we have a force that's at an angle, we want to find the x component, which is f cosine theta. And then we just multiply those two, f cosine theta times the displacement. And like I said, it gets rewritten like this. Now, this equation is on the reference table in a variety of different ways. It's written like this, that the change in energy is equal to the work, which is equal to force times the displacement, but this is the force parallel to the displacement, or it's FD cosine theta. Like I said, in a lot of cases, if you have the force, if they tell us that the force is acting in the x direction and it's moving in the x direction, so that they're in the same direction, then we don't have to add that cosine theta. We just simplify and say force times displacement. If the force is in the opposite direction, we have to make the qualifier that the force is in the negative direction or displacement's negative. One of those two is negative. Um, So we could do that and again not have to worry about the cosine theta. But if we do have the theta, we have to make sure that we add on here. It is extremely important though that we keep track that the theta is specifically the angle between the force direction and the displacement vector. So those two are are the theta that we're talking about. If let's say this object was being displaced upwards, then this is not going to be the theta that I use in that equation. I'd have to find the angle uh, in this vertical direction. So this angle, the complementary of this theta. Just keep that in mind, though usually it's not going to be a big thing. So one question I could ask is, does this object, is this person doing work on this box? He's lifts the box up, carries it to the desk horizontally, and the question is, does he do work, and if so, when? And the answer is only when he lifts the box up. When he moves the box to the side, he is technically not doing any work because the force being applied to the person is acting upwards while the object is being displaced to the side. So this is a 90-degree angle, so cosine 90 would end up getting 0 degrees. So the work is 0 during the moving side to side. It is only when you're lifting it up and down that the force that you're applying is doing work. So work on this question. Pause video, works up. We'll go over in a second. All right. So starting off strong, they want us to know how much work we do in this scenario. We're slowly lifting a book up at a constant velocity. Because it gives us this qualifier that it's constant velocity, that means that the object is in equilibrium. So the force that I'm applying is equal to the force of gravity pulling it down. Keep that in mind that that we don't have to have a force that is greater than the gravitational force to lift an object up. We can lift it up with an equal force as long as we're lifting up with a constant velocity. So the force acting on it is 20 newtons. The displacement, it's being lifted up 3 meters, is 3. I don't have to add on that cosine theta because they're going in the same direction. So my work ends up being 60 joules. Positive means that I'm adding energy to the system. What work on this one? Pause video, works up. I'm going to go in a second. All right, so now we have a person pulling on a rope 30 degrees. They tell us what the tension force is, and we want to know how much work is being done on the crate by the worker. So because we have the rope that's pulling at 30 degrees, the angle is given to the horizontal. The crate is sliding horizontally along the floor. So this 30 degrees is going to be acting on so one way I could do it is I can do my FBD stuff. I could break up Fx into its or the tension force, the applied force into an y component, x component. That x component being F cosine theta. So the x component would be 60 newtons. And then I could plug that into my work equation, multiply it by 10 for the displacement to get about 600 joules. The other thing I could have done, I didn't do it here, but I could have done F d cosine theta, plug it all in. Again, it doesn't really matter. It's whatever floats your boat. The only issue with doing the FD cosine theta is if they ever throw this curveball where the theta is not being given between the force and the displacement. It's not super common, but it happens, and it's one way that the AP can make the questions a bit trickier. If you want to try to avoid those, if you what you could do is, like I said, just always set up an FBD, break up the forces, all that stuff, and then find the force that is going in the same plane as the displacement. If you do it this way, you'll never get the question wrong because you'll always be finding forces in that specific dimension. So that's kind of the idea behind why I showed this way. All right, so here's the next part. Pause the video yourself and go in a second. All right, so they want to know how much work is being done by the normal force. The normal force is acting upwards, and you might think that you have to actually do some work to find the normal force, except we don't, because the object is being displaced horizontally. The normal force is acting vertically. That is at an angle of 90 degrees. So when we do this, we end up getting 0 joules. Now, I went through the extra steps of actually finding out what the normal force is to show that it doesn't matter. No matter what that normal force was, it was always going to be 0 because cosine 90 degrees is 0. All right, here's the next video. Pause the video work itself, and we'll go over in a second. All right, so here they want us to figure out the work being done by the frictional force. The frictional force is acting in the plane of the displacement, so I will be able to find a force for this. I can just make it so that the force is negative. I don't actually have to do the cosine theta part again. But in order to do this, I need to use this coefficient with the normal force. And this is actually one of the reasons why I actually found the normal force in the previous part. Again, we use our go-to sum of the forces in the y direction. The sum of the forces in the y direction is going to be equal to 0. So the gravitational force pulling down minus this force pulling up is going to be equal to the normal force. So I take the normal force from the previous part, multiply by zero point 0.4, and I end up getting 46.2 newtons as my frictional force. Now, if I did want to do use cosine theta, I'd have to make sure that the theta is now 180 degrees because the displacement is going to the right. Well, they don't specify that's to the right, but based off my FBD, it's going to the right in the opposite direction of the frictional force. So that is a 180-degree difference. So you get a work done by friction of negative 462 joules. For the most part, as far as now, you should be able to just use the equation, and it really depends on just paying attention to what force they're referring to and whether that force is in the plane of the displacement or has a component in the plane of displacement. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.